All right. Hello, guys. Welcome to sword counting part 2. Hopefully we can figure out this time. But all you guys already know the problem, right? Like, you understand what the problem's asking? No? Okay. That's fine. So we have a structure. They give us a structure which looks something like this. So this sort of structure is called a sword. And they want us to find within any graph how many swords are in that graph. So AKA, how many of these structures are in that graph. That's pretty much what we're trying to find.
Oh, like in a graph, find that type of structure?
Yeah, exactly. So if we have something like this, how many swords are here?
Small question, does it also have to be like 2 dots after the little, like?
Yeah, it has to be exactly like this. One of them needs to have 4 neighbors, then another one needs to have 2 neighbors, and the rest needs to only have 1 neighbor.
Wait, I only see one. I don't know if I'm crazy.
So keep in mind that it doesn't have to be straight up. It could be to the side as well.
You're 7.
For 7, you counted?
Yeah.
7?
At least 7.
Are you bullshitting us?
I see 7. Okay, that's good.
Wait, what? No, okay. Show me the 7, cause
All right.
okay. So yeah, that's 1.
1, right? 2,
Oh fuck, my clown ass.
3, 4,
Oh fuck. Okay, I feel dumb.
5. It's fine. 6, and then 7. Okay.
Did nothing for me.
So, what's something special about this graph that you guys can see in it?
It's a tree.
Yeah, nice. It's a tree, exactly. That's really important. So, in the cases where it is a tree, it's pretty simple to find the number of swords. You find the node that has at least 4 neighbors. So it needs to be greater than or equal to 4. And in that case, huh?
Degree 4.
Yeah, degree 4, yeah, 4 neighbors.
Yes.
Okay. So I think I wrote this notation down last time. Let's make big U equal to, for all the nodes inside of V, if degree of U is equal to 4. So let's say U, capital U, is equal to all the nodes that are within our graph if the degree of that node is equal to 4. So now for all of those nodes, we're going to want to run or do some logic, which is going to be degree of U minus 1, choose 3. Do you understand why we're doing this part? Oh crap, you weren't here for the previous two. Okay, I'm sorry, I just...
Not really, because he was explaining, I was like, what?
Yeah, okay, I just realized that you also weren't here for the previous lecture. Okay.
So why is it degree minus 1? Why?
So, because one of them is going to be chosen as the blade. First, let's set up some vocabulary. This node right here that has 4 neighbors, let's call that the middle. The 3 next to it only have a degree of 1, let's call that the hilt. And then the one that connects to the node that has a degree of 2, let's call that the blade. And then this one, let's call that the tip, right? You can see how that kind of works out if it's an actual sword, where this is just the middle of the sword, this is the hilt, the blade, and the tip. So why are we doing degree of U minus 1? Well, realize how I mentioned that for every middle node, it needs to have a minimum of 4 neighbors, right? For it to actually possibly be a sword. We want to subtract 1 because one of those neighbors is going to be part of the blade. So of that degree of that middle node, minus 1, let's choose 3 to see how many different combinations of hilts we have. So that's how we're kind of starting off the sword, the graph, seeing how many ways can we make the hilt with its neighbors. And then with the remainder, I guess I can write, yeah, let's say B is equal to B. Give me a sec. I know this is pretty quiet right now, but okay, cool. So that's the rest of the code. So if we just constructed the hilt using this logic right here, we now want to see how many ways can we construct the blade. Okay. To construct the blade, we first have to choose all the neighbors that have a degree greater than or equal to 2. That part makes sense? Because the only way for it to be a blade is if it has at least a degree of 2. Cool. So now we multiply whatever this gave us times the degree of the blade minus 1. The reason we subtract 1 is because we don't want to include this edge that goes back to the middle. That minus 1 is going to tell us how many different tips we can have. So if we want, we can run through an example. Simple example. And for this case, we only have one middle.
You could just say that the first loop is looking for the, wait, what is the H mean, hilts?
Yeah, the hilts.
Yeah. First loop is looking for the hilts, and the second loop is looking for both the blade and the tip.
Exactly. So this is what that part is doing right there. This just tells us all the possible hilts for that sword structure. And then, like you said, the second loop is usually tell us different combinations of tips, considering B as our blade.
Oh, yeah, okay.
Cool. So you're good with that?
Yes.
Okay, nice. But there is one issue, like you mentioned out, this only works for graphs or a tree. It's a little bit harder when it's not a tree. Do you want to guess why? Or do you know why?
Oh, because what if that's already, if the halt is being, the node is already being used?
Yeah, exactly. So what if we're trying to construct where the blade is this node and then the tip is this one? That'll be invalid because this node was already used as the hilt. So we're trying to overcome that. And that's what Giri talked about yesterday during his lecture. Demba, David, Joseph, you guys are good? You guys understand everything up to here? Yeah, all right, cool. Okay, well, just making sure like no one was looking at it.
So wait, wouldn't you just, I guess, keep track of what's being used as a halt then, or whatever?
Yes, kinda, in a way, but since we have the number of nodes we're given is less than or equal to 10 to the 5th, and the number of edges we're given is less than or equal to 10 to the 5th, keeping track of that might be pretty expensive. Mostly like just searching. If we considered every middle, and then we also want to look at the neighbors of the middle and also look at the neighbors of the blade, our time complexity is already horrible. Okay, cool. So what did Giri discuss? Anyone want to give it a shot? What he talked about yesterday? How could you?
He counted like the intersections between like
Yeah.
two nodes, right? And then that will be the number of intersections will choose the with that
Yeah.
value different, assuming they intersect, how many will overlap or subtracted from the and choose the first value?
Mm-hmm. Yeah, so he put it out nicely in one big formula, by just assuming we knew that K, or we knew how many triangles are formed if we take B as our blade and then M as our middle. So David also got it right. He was putting up the triangle sign with his hands. So yeah, we're basically counting the number of triangles for this blade and this middle. I'm going to be doing it a little bit differently. I'm not going to go over his formula. I also don't really remember, but I think it was degree of u, choose 3. Times degree of b minus 1 minus k. Where's the k prime? Is the k prime here? Oh wait, I can just look at it. Oh crap, I can't look at it. Wait, I want to switch it up now. There was definitely a k prime, if I remember correctly. The k prime is either with the degree u or part of the degree b thing. Okay. Okay, I don't think I got it in frame. Oh wait, here it is. Okay, cool. Oh, times k prime minus 1. Okay. This is what he had. Times k prime minus 1 plus okay, cool. Degree of u, choose 3 times k. All right, so, and then here where k prime is equal to degree of b minus k. Kind of had it right. I think I was just missing this part. So this is what he showed, but I'm not going to be going over that. I'm going to be going over it a little bit differently and showing you guys how to code it out in a different way. All right. So the basic recap of what he went over is doing this with looking at the edges. If we're looking at just edges, then we know we are for sure looking at 2 nodes that are already connected together. At that point, we only have to find one more. So that makes it a little bit easier for us because that allows us to have a time complexity of big O m times n, where m is the number of edges and then n is the number of nodes. For example, if our given edges is 1, 3, 2, 4, 4, 5, 2, 5, and 6, 9, we can just look at the first edge. We already know they're 1 and 3 are connected together because we are looking at edges. Then at that point, we can just iterate over all the number of nodes and see if one has is adjacent to whatever node we're looking at. Let's say we're looking at the first edge, so we're looking at 1, 3. Now we're going to iterate for u in v. If the neighbor of 1 intersection u, the cardinality of that is greater than 0, we know that u is part of the set of neighbors of 1. Therefore, we know that U and 1 is connected. And the neighbor of 3 intersection U is greater than 0. If these two cases pass, then we know that U is both a neighbor of 1 and 3. Therefore, we know we have a triangle. Does that part make sense? I guess I can draw it out to make it a little bit nicer. Say I have 1 and 3. The current edge we're looking at is this one right here, this edge. So now let's say we have multiple nodes. We're going to first look at this node, see if this node is connected to 1. If it's not, we know we can stop early. Now check it with this node. There's no edge. Check it with this node. There is an edge between 1 and the current one we're on. So now we have to confirm if this one also has an edge to 3. If that's also true, we for sure have a triangle. Okay. And that will give us that time complexity of big O of m times n, because m is just the number of edges, and then n is the number of nodes in our graph. So what's one way we can rewrite this? David, tell me. I feel like David has the answer. What's one way we can rewrite this?
M times n?
Yeah.
M is, what is that?
Huh? M is the number of edges.
N is the number of
Yeah.
vertices.
What? No, I said edges.
N.
Oh, n? Yeah, vertices.
Okay. Rewrite that as O of V times E.
No. Okay.
Something.
2 times something? Okay, that's actually later on.
Oh, wait, not yet? Oh,
Yeah.
Never mind.
Demba, how about you? I feel like you know it.
How do you
Rewrite this, yeah.
O of m times n?
Yeah. I think you can rewrite it to this, pretty sure. Huh?
O of e times e?
No. Okay, so I'm just gonna write it out.
I don't see.
And you guys let me know. I'm pretty sure he said this during the lecture. Whoops, that's a horrible sigma. Edges. You guys remember this?
Oh, the square root of m times.
Well, okay, not yet. Yeah, eventually we could reduce this to that. Or we can reduce it to something else. But yeah.
Yeah, I completely forgot.
Yeah. He did say this, right?
I remember enjoying that. I'm not gonna lie, I didn't even know what the question was, so I was just kind of like reading along.
Okay.
Cool.
So yeah, that's another way of rewriting this. Because he said that, Dr. Geary said that this time complexity is pretty much our base, and from there we're gonna do some analysis to just bring it down and see what it really represents. All right, so after this he made another pretty big claim, or at least I thought it was pretty big. If we're doing this computation for each and every single one of the edges we're given, what we're basically gonna do is degree of 1 plus degree of 3, degree of 2 plus degree of 4, and so on and so forth. I'll just go ahead and finish this because I might use it later. If we're doing this computation is for all of the given edges, we have something that looks like this. But like he said, this boils down to something pretty neat and pretty cool. Does anyone remember what he said? Yeah. So at least to me, that was pretty crazy. I don't know if I'm the only one. But if we do this, this is basically saying, which is what we're doing right here. That's basically saying the same thing as dw. as saying that. It's the exact same thing. And we can actually prove it, which I will show you now. But first, let me draw out this graph so we all have some representation or an idea of how it looks. All right, so this is how our graph looks. I hope you guys can all agree. If you look at the edges, 1 goes to 3, 2 goes to 4, 4 goes to 5, 2 goes to 5, and 6 goes to 9. So now let's evaluate this. David, you want to give me the first one? Yeah, here's the graph, so make it easier for you.
Square root.
No, this.
That one.
You have to pay attention, dude.
1 and 3. Well, that's 2.
Yeah. This would be 1 plus 1, which is equal to 2. Joseph, you want to give me the second one?
2 plus 2 is 4.
Yeah, 2 plus 2 is 4. Dembo, you want to give me the third? 4 plus 1?
No.
Oh.
I'm saying the degrees. Degree 4 plus degree 5.
Yeah.
That's 2 plus.
All right, Daniela, you want to give me the next one?
Damn, he really said she got on her phone. I better ask her.
I didn't even see it. So
Uh,
this one, yeah.
and what was 2? Where's 2 at? Oh, that's 2.
Yeah.
And then plus, wait, what, is that a 5?
Yeah, it's a 5.
What is that? Oh, 2.
Okay. So 2 plus 2 is also 4. And then David, going back to you. What's the first?
Also 1 plus 1.
Yeah. And we add all this up. That gives us what, Joseph?
Oh, 8, 12.
What the heck?
Oh, that's
My
not
bad.
12, 14,
16, yeah. This will give us 16. So I think we can all agree using this method, we will get 16. But let's see if we do it a different way. If we do it the degree of u squared, let's see if that gives us anything different. I am going to go ahead and write it right over here, I guess. Do it in line. Degree of 1 squared, degree of 2 squared. Did I miss one? I did 1. Yeah, degree of 3. All right, cool. So, all right, David, give me the first one.
1.
I just turned the camera on. Yeah, the first one is 1 because it's just 1 squared. Dembo, second. Joseph, third.
Wait, I wasn't paying attention.
Doing this part?
Degree of 4 squared.
Yeah.
That's 2 squared 4.
Yep. David?
So it's 3, right? So that's also 1 square 1.
No, that's 5.
That's 5?
Yeah.
Oh, okay. Then that's also 2 squared, that's 4.
Okay, cool. So if we add all this up, what do we get? We get 16. And it's exactly the same as this, as what we did over here. Now why? Why does this make any sense at all?
Black magic.
No, it's not. It's not black magic. I'm gonna go ahead and delete this part. You guys can probably remember it. If not, it's right there. I'm also gonna redraw this graph a little bit smaller.
Oh, God, I am clicking on you.
Oh, you have to go? It's all right. Don't worry.
Thank you.
All right, take care. Thanks for coming. Have a good day.
I'll do my best to go to
All right, so that's the exact same graph. Just redraw it, made it a little bit smaller. She's my neighbor. So. I'm kidding. I don't know why she said that. All right, so that's the exact same graph. Now let's explain why just taking the degree of u squared is the exact same thing as taking the degree of u plus v squared, where uv is an edge on the graph. One thing to take into account is initially we were processing every single edge and then looking at every single node in the graph. So let's give us an example. Let's say we have some node u, and it has 4 adjacent nodes. Therefore, it has a degree of 4. Since we're going to be processing all of the edges, we're going to do each and every single one of them one by one. First, we're going to process its top left edge, and we're going to compute the degree of u. So I'm just going to write it here. That's going to be let's make this a little bit simpler for you guys. So let u be node, this one right here, with 4 neighbors. So we'll be processing each and every single one of the edges. We're going to do each and every single one of them at a time. Since it has 4 adjacent edges, we're going to compute one of these edges 4 times. In this scenario, we have to get the degree of u. The same thing for each and every other scenario. In this case, we're going to be adding all of them up. Because remember, each and every single one of the neighbor goes to some other node, but we don't really care about the other node. Because initially, we had that big O time complexity, where for every edge, uv, we're going to sum u plus the degree of v. And I'm showing that here, but I'm just dropping the degree of v because we don't care about the other node. I'm just simplifying it to prove to you guys that this does work out. So in this case, let's only look at the degree of u. And once we add all of them up, we're going to have 4 degree of u. Well, what is degree of u? Does anyone want to tell me? 4. Degree of u is 4, therefore we get 4 squared, which is 16. So since we're processing each and every single edge, we're going to see the degree of u for node u, degree of u amount of times. Therefore, we can just simplify it to the degree of u squared.
So it's the sum of all the degrees of all the nodes.
Yeah, since we were trying to do the big O mn, we have to do the sum of all of them.
Okay.
It's not just one node. So now does it make sense why this and this is exactly the same? Or in other words,
So would that be all n squared?
no, I don't think so.
Oh, actually no.
So now we just proved that this big O notation is the exact same thing as this one over here. Yeah, it wouldn't be big O of n squared because it's m times n, the edges times the number of nodes. It could be the case where it's n squared, but that's if the edges is the same thing as the nodes. Yeah, sounds good. So we just proved that part. Does everyone understand this, or have I convinced you guys that this is true? Or is there any confusion? Let me know, because I was confused on this until I drew it out like this. I think this representation of this graph really helped.
It makes sense because every node will be connected the degree number of times to another node.
Exactly. Yeah. Joseph?
I don't think you proved it in the sense that degree of u plus degree of v on the left-hand side, those 4 nodes that you have, how would you represent that? There's no other degree of v.
This is because I simplified to just one node. You can think as the degree of v as another simplification. That's going to boil down to the exact same thing.
So where's degree of v? You're counting it as a node with 0?
No, degree v is somewhere in this graph. It's just I didn't draw it in because we're only considering for one node. If we consider degree node v and we do the exact same process, we will be getting the same thing. It will come up to this exact same thing.
Yeah. You know what you can do? Just change one of those used to be a v.
Sure. Or you can just change it here as well and then make the exact same assumption. All right, cool. So, all right.
So this only applies because because it is a connected graph, but regardless of that, it applies because the number of degrees when we take that into consideration.
Yeah. Okay, cool. By the way, for this graph, that u that I was showing was not part of here. In this case, the 16 matched just because that u had 4 neighbors. But that doesn't mean that that one single node represented all of this. That was just an example.
No, I know.
Okay.
I'm just saying, like, for you to prove it with one node, like, there's no purpose of it. If the
Yeah, there is.
Is u plus v.
No, but it's the exact same thing. That one node, I'm showing the process for computing that one node, for that node u.
Yeah.
But for node v, it's going to be the exact same process. So therefore, it's going to evaluate to the exact same thing, whereas it's just the degree of that node squared.
Because every v would at some point be a u.
Yeah, exactly. I could have made it a little bit more abstract by just saying, let u be node here with, I don't know, p with degree of u being p. That could have made it more abstract because now I'm no longer just considering 4 edges. I'm considering any amount of edges. And there you could have applied it to any node in the graph. But that was just an example with 4 neighbors. Okay, so let's go over this.
You know what I think might help? If we draw like 2 nodes and then connect them like a
Okay.
graph with just 3 nodes and then do the computation.
Yeah, that's what
So let's do this graph, right?
I mean, I understand it, but I'm just saying, like, for you to prove it,
Hmm.
I think it would be better if you do, like, 2 nodes.
2 nodes, okay.
To u and v for, like, 3 nodes, and that's it.
So we're going to be doing one component of this graph that we were given. For node 2, we're going to compute 2 of its edges. So we're going to be having degree 2 plus degree 2. And that's going to be 2 degree of 2. And this will be the exact same case for every other node in this component. So this will be degree 4 plus degree 4. And then degree 5 plus degree 5. Now, what is this going to evaluate to? It's 2 times the degree of 2, which is what?
4.
Yeah. This will be the exact same thing for the other ones. So that's why I only showed one node, because it's still the exact same process. The only thing it's dependent on is its neighbors. So that's why I did that further abstraction by just saying a node u where the neighbors, or the degree the degree of u is equal to p. Does this make sense now, at least doing it for this example? And you have that 4,
Shouldn't it be,
which was right there.
shouldn't it be times instead of plus?
No. Why do we plus?
It should be degree of u squared.
But we're doing the summation.
Or you're doing this
Yeah.
with v.
Yeah.
It shouldn't
No,
be-
no, no. So for every single edge we're considering, right?
Well, what do you have to, consider the same edge?
Consider it the same vertex.
Same
Yes,
node,
because
node.
yes, because first we do this edge, right? And then later on, where does the second degree of 2 come from? From this edge. So okay, I can break it down a little bit more, like to fully expand the thing.
I mean, I get it. I just didn't get the point that thing was proving.
This first part is for this edge. The second part is for that edge. Then the final part is for that edge, using this approach. But now we can group them by their degrees of 2's. Therefore, we have 2 degree of 2 plus 2 degree of 4 plus 2 degree of 5. Each and every single one of these nodes have a degree of 2. Therefore, it's just be 4 plus 4 plus 4, which is 12. And it does match with what we have here and here. But what I did was doing it this way, where for every single edge, I just broke it down, and I knew that it's going to be degree of u, or degree of 2, times how many edges it has, or degree of 2 squared.
Why are you multiplying the degree of 5 by 2?
1 and then 2. There's 2 of these from here. So degree of 5 plus degree of 5, you can think of as x plus x, 2x.
Yeah, but aren't you supposed to be squaring?
It's the exact same thing. It's going to come out to the exact same thing.
Well, I mean, it's the exact same thing in this case because they're 2's. But if they weren't 2,
Okay. So
like if they were 3, it'd be 3.
remember when we were doing this one with 4? You think it was going to be different for this?
No, I'm saying that like when you multiply it by 2, it's not the same thing as squaring it. Because you're
Okay.
getting like on the bottom line. You have 2 times the degree of 2 plus 2 times the degree of 4 plus 2 times the degree of 5. And it should be the degree of 2 squared plus the degree of 4 squared plus the degree of 5 squared, right?
This will come out to the exact same thing. You agree with that?
Yeah. No, yeah.
Okay.
I know it's one system.
Let's augment our graph a little bit more. You think this will be different now? Yeah? Okay, let's do it.
Oh, but you're doing 3.
Yes,
I thought you were
because now there's 3 different edges.
Yeah, I thought you were going to keep like 2 as a
No,
constant.
no.
Oh.
No, that 2 is coming from the amount of edges we're processing.
Yeah. Well, you could just square it.
Yeah, that's exactly why I do at the square.
But yeah, sure, whatever. Yeah.
Because this, you're going to get something like a, or let's make it better so we don't get confused, alpha degree of u, where that alpha is exactly equal to degree of u. Therefore, we can just say it's going to be degree of u squared. All right, cool. Thanks for cutting me off before writing all of that, by the way.
No, yeah. I just thought like 2 were just like.
No, yeah.
For some reason, I was like, oh, like, are you doing it by mistake? Like 2 representing the squared? Like, I mean, yeah.
Yeah, 2 just comes from those edges.
Yeah. Okay. Yeah.
All right, so now let's dive to some more graph theory by making a note. Does anyone know what this is going to equal? 2m. Why?
We have those many edges, like all the degrees. If you sum up all the degrees, they're gonna, like if you sum up all the degrees in an undirected graph, they're gonna have to be 2 times the number of edges.
Yeah, so all edges are counted twice, pretty much. That's why it's 2 times m, where m is the number of edges in a graph.
That's only because it's an undirected graph, right? It goes both ways.
Exactly, yeah. If it was direct, it would be different. So let's boil down what this is going to come out to. This essentially, for every single node in our graph, is going to be equal to d1 squared and there's, since we have 7, I would write 7. So this is exactly what we get for this graph right here, where d of 1 represents the degree, the first node, d of 2 the degree of the second node. I know it doesn't really match with the label of that node, but yes, assume it does. You know what? I'm going to change this to 7, to 7, and then to 7. And also change that up here. Make this 7. So now each and every single subscript matches the label of some node in our graph. Now let's make another note. Something else that we have to take that we have to mention or take into account is that for every or for any d of I, it needs to be less than or equal to the square root of m. Why? Anyone want to tell me?
Why every I would be less than the square root?
Yeah.
Because if every I was greater than the square root, if some i's were greater than the square root of m, the summation would be more than 2m.
Sure. Let's go with that. Yeah, that I guess that's fine. Yeah, let's just go with that and say that's fine. So if with this taken now into account, we can further expand this, where it's going to be d1 times d1 plus d2 times d2. I'm not going to write all of it. It's too much. So now we're going to have something like this. I'm just expanding it. It's going to be the exact same thing. Hopefully you guys agree with that. And let's make one of them. Let's make, for example, the second of the pair. For each and every single pair we have, let's make them square root of m. Now this is the part that confused me, to be honest, because if we're saying that one of them is square root of m, then we must also assume that the second is square root of m. But I guess that kind of works out, because if that is the case, we have m times n, which if you remember, was our original time complexity. If you have to go, you can go.
Yeah,
Okay.
I'm gonna go see Azar.
All right, take care.
The doctor.
Azar.
Oh, maybe I should see a doctor actually.
Take care, man.
So, but for now, let's just assume that one of them is square root of m. What does that mean? What must the other one be?
If one of them is square root of m.
What?
No,
Because
they-
it has to be less than or equal to the square root of m. So if one of them is square
No.
root of m, the other one has to be 1.
The other one has to be the square root of m or less.
Wait, I don't think I get it. I think I'm kind of lost. Because if
Well,
what
look,
I'm getting is true, right?
When you square anything, right, to revert it back, you get the square root of it. If you add anything on top of that, then when you square that back, you get the square root of it. The only thing is, it's the less than, because 1 squared is still 1. So when you square that back, when you square root that back, it's less than or equal to the square root of m.
No, like what I'm saying.
I don't know, but that's coming from a math minor right here. Certified
Yeah,
math minor.
I have no idea what is talking about.
All right, I think I can.
But like my problem is, you see, d of I is less than the root of m, right?
Okay, dude, look, do this. 5 squared, what's 5 squared?
25.
Okay, plus another node that has only 1. Or like, let's say plus another that has like 2. 2 squared. 4. 25 plus 4 is 29.
Yeah, I think this helps.
What's 29 squared? What's the square root of 29? Okay, the square root of 29.
Okay. You can just see it visually from this. If you have some a squared and you're trying to make that equal to less than or equal to c, and you want to break it up into where one part is c and the other one is b, that b needs to be less than or equal to c. Oh, sorry, less than c.
Okay, so a squared is less than equal to c, right? So b times c is less than equal to c. So you need to make sure that b is less than c, and then when you multiply b and
Wait, what the hell?
Nah, that's wrong.
That doesn't make sense.
Because if b is less than c, when you
It needs to be
multiply
1.
b times c,
It needs to be 1.
that's what I was saying, it has to be 1. In my head, it has to be 1.
Okay, I think it's because.
It's not even gonna
No,
be
it.
it's gonna be exactly equal to the square root of m.
I think that makes sense.
You think it will make sense? This?
Huh?
This makes sense?
Does it?
I don't know. Let's see, a squared is less than equal to the square root of c.
Oh, I remember now. He made it equal to.
Plug in numbers, let's see if it works. Plug
Oh,
in
that's
numbers.
2m.
5 for A and then 6 for 36 for C. And test it out.
Huh.
Plug in 5 for A and 36 for C and test it out if it works.
36 for c?
Yeah, because
6?
square root of
Okay.
36 is 6. No, that's not even greater than A squared. Wait, hold on. We can find, what's the square root of 26?
yeah, I think your proof is wrong.
Yeah, I think that's wrong too. No, it for sure definitely is wrong.
Where'd you get that from?
No, I just came up with it. Yeah, it have to be less than 1. Less than or equal to 1.
Yeah, that makes sense.
No, but even the
Even if all these are squared.
the degree of any node is less than or equal to the square root of m, where m is what? The vertex, is it the vertices or the edges?
Edges.
The edges. Oh. Yeah, that still is
Wait, what?
1, 2.
Wait, can
Okay.
you go back to the D1 plus
Yeah,
D2?
that-
Let's see what we're trying to do there.
I don't think.
Where? Here?
Yes. That's the square root of the
Yeah, so this is us expanding this part, right?
Okay, so what are we trying to do down when you have D1, D1?
Yeah, okay, so now he broke it down to just separating the square root. And he's going to assume that every d of I is less than or equal to square root of m.
And when you say D of I, do you mean both of them or do you mean just one?
Yeah, that was my exact same question too. If we say that one of them is square root of m, then why do we not say the other one is square root of m? If they both represent the same degree.
Let's assume one of them is square root of m, right? If we sum everything up,
Yeah.
just one of them being square root of m, we're going to have m times the square root of m, right?
Wait, give me a sec.
Guys, I think the proposition itself is wrong. Because I can find you a graph that has a vertex.
No, this is not wrong because the ICPC released it and they say the same thing.
No, but so what is d of I? The degree of a node is less than or equal to
Yeah.
say you have the degree of u squared with your
Alright.
sum of all the edges.
Fucking hell, I can see my fucking pen.
So we break it down to this. It eventually equals to that if we just make one of them equal to square root of m. I'm not totally sure on this part, to be honest. I couldn't really figure this part out too much.
The square root of m would be n times the root of m, right?
Huh?
The square root of m, like if you sum up just the ones with root m.
This one?
No, down, like where you have the root m for, when the root m is replacing one of the these.
What?
Like, right there, bro, like
You-
one step up, one line up, that thing, exactly. If you sum up all those root m's, what are you gonna end up with? N times root m? Like the number
You're
of
gonna
values.
add up with, come up with this. I just factored out the square root of m.
You fucked it out the square root.
Yeah, and that's where we get the 2m to the 3 halves. All right, so this is what he proposed. And now if we take care of these edges, or at least separate them by the ones that have a degree of less than square root of m, and the ones that have a degree of greater than or equal to square root of m, our big O notation is just going to be m 3 over 2. And that is doable with the constraints we have. So that's the most important part, where we want to break up these edges into two different lists, or vectors, where one vector contains nodes or vertices that have a degree of, for example, in my code I did a degree of greater than or equal to the square root of m, and the other one is less than. You want to write it?
A node with degree 3, right? And there's 3 edges. And your square root is less than. Right? It's less than that.
What do you mean?
That's not true. I don't know. I mean, maybe I'm looking at the question wrong.
This one has a degree of 3.
Yeah.
And then if you do what? If you square root this,
If you square root the m, which m is 3 because it has 3 edges, then you get a number that's 1.7. And 1.7 is larger than 3.
no, what he had over there is d of 1
Uh-huh.
times root of m.
Times? No,
Because,
isn't it less
because
than?
it's replacing.
No, I'm multiplying it.
Wait, what?
because
Wait, what's d of I?
D of I, he's making one of these square root of m. So what he has there is also correct.
When you join two nodes,
What?
what's d of I?
The degree of one node.
The degree of one node?
Yes.
And
But now we're breaking this up and saying that one of them is equal to square root of m.
and one of them, one node.
Exactly, yes.
Is
Yeah.
equal to this, is equal or less than the square. I just have a graph right here that is literally proving it wrong. 1, 2, 3,
Mhm.
right? This guy right here has an integrate of 3,
Mhm.
right? When you get
For each and every
when you
single one of those nodes, just do that and see if it comes out.
No, but like there's this one vertex right here that's wrong, right? This one.
No, you have to do it for each and every single one of them. Do all of this. Do this part at least. Square root of m, then the degree of 1 plus 2 and 3.
Wait,
And see if it equals to 2m 3 halves.
so the square root of m times all the degrees.
M is all the what
All
is
the
it? M
edges.
is all the
Edges, yeah. So do that part and see if it works out. All right. I'm getting pretty close to time. I don't think I'm going to be able to show the code, but at least we discussed about the triangle.
Do you guys remember the probability mass function thing in stacks?
Say that again.
Probability mass function, PMF? Yeah. That doesn't make any sense.
I mean, yeah, that statement is true.
It comes out? Yeah, so that's what we're trying to make, that this statement is true. It's not just one thing. It's the whole thing. So yeah, this does hold. All right, so yeah, now we can break up, for every vertex in a graph, we can break them up into either heavy vertices or light vertices. I know ICPC defined heavy as greater than or equal to the square root of m, and then light less than square root of m. And now for each vector for heavy and light, try to see if you can find 3 heavy vertices that make a triangle. And then for light, find only 1 vertex that is a light vertex. And then try to find a pair of its neighbors that make a triangle. And that will bring you down the right path for solving the question. That would get rid of the triangle issue. Yeah?
One is n and the other one is m.
No, both of these are m's. So you could have a vector called heavy and a vector called light. The vector called heavy is going to be full of nodes that are greater than or equal to, that have a degree greater than or equal to this. The light vector is going to be nodes that have a degree less than this. And then for every node in heavy, try to find 3 heavy nodes that make a triangle. And then for every node that is light, try to find a pair of its neighbors that also make a triangle. And since the time complexity is going to be m of 3 halves, it's doable with our constraint. All right, sounds good? All right, and that's all I got. So that's why he summed up. Hopefully you guys understand it better now. So yeah. I'm also be ending the live stream because we're getting pretty close to time. So thank you guys for watching. Hopefully this helped, and good luck on the code. We're going to be putting out a competition for FAU competition on Saturday. It's most likely you're going to have this problem, and I love strings. So you try to solve one of them. And we're also going to have regional practice. We've been having regional practice for the past 3 or 4 weeks. So continue doing those because the ICPC competition is coming up.